Alright, hell yeah. So what we have here is a very difficult integration by black pen, red pen. Now, we're not going to do anything complicated at all. We're just going to do what no one does. It's kind of an analytical approach. So with this, we do have two different variables going on, but this is just kind of the number that we want. So we're going to say, hey, this is the number to the t, and that's the equations. We could say like this is y, some sort of number to the t. For whatever reason, t just doesn't set in with me very well. And so we're going to do this, some number to the x. And you're just like, oh, hell yeah. And then so the strategy that I employ is this 0, 1, 2. Sometimes it works out pretty well. You know what I mean? Just throw in a value and see what you get. You know what I mean? So we're going to choose y is equal 2 to the x. And then we're going to start graphing this. And so 1, 2, 3, 4. 1, 2, 3, 4. There you go. And then, so we're going to throw in 2 to the 0. So right at 0, 2 to the 0 is 1. So sweet. And then 2 to the 1 is 2. So we come over here to 1, and then we go up 2. And then when we go 2 to the 2, we're going to be all the way up at 4. So there you go. And we have a simple little graph maybe. And so even right now, we can figure out what the integration is. Integration is just area under the curve between 0 and 2. So there's 0 and 2. I'm just going to make little boxes. Okay, so we have 2 boxes. Oh, look at that. We have 3 complete boxes. So this has to be greater than 3. You know what I mean? Booyah. And so then what we do is just, hey, let's just reduce this. So we're going to go y is equal 1 to the x. Okay, so 1 to the 0 is 1. 1 to the 1 is 1. And then 1 to the 2 is still 1. You know what I mean? Just like over here. 2 to the 0 is 1. 2 to the 1 is 2. And 2 to the 2. Those are the points that we threw in. So now here, our graph's going to be 1, 2. But then just it's going to be 1, 1, 1. And this is our line. We're going to integrate between 0 and 2. And check that out. We got 2 boxes. So this is equal to 2. And so this is such a cool method for finding solutions. One, you were like, let's say you were like 4. You know what I mean? So you had a solution of 4. That's not 3. And then we changed our value. And then we get a solution of 2. Well, you know, it has to be that the solution is in between there. So then we choose like y is equal to 1.5x. You know what I mean? So we have 1.5 to the 0, that's 1. 1.5 to the 1, that's 1.5. And then 1.5 squared, that's 225. Or I mean 2.25. So let's graph that, and we get 0, 1, 2. And we'll go 1, 2, 3. Because we have start at 1, and then we're going to go up to 1.5. And then we're going to go up to pretty much just 2, but 2.5. Okay, so here's our graph. We have a full box there, a full box there, and let's see, what else do we have? And then this is where I was just like, well, let's say this is right around 2, and this is, so we almost have a triangle that's 2 by 1. So this is a dimension of 2, this is dimension of 1. Hey, that's about an area of 1. So look at that. We pretty much have it that this is pretty close to 3, and we could be done right here. We know there's a little bit extra, so maybe it's like 1.6. You know what I mean? So you could get there just that fast. Okay, so this was the quick version. Now I go into the actual video that I made yesterday, and we talk a little bit about what integration is. But I just wanted to make a quick version just right at the beginning of my videos, because hell yeah. Alright, hell yeah, a little addendum at the end. I don't know what the hell I was even saying. The whole thing is just to make this easier. If this is 2.25, this area is going to be way bigger than, you know what I mean, 1. And then so we do have to reduce our number. So we're going to have like 1.4 and, you know what I mean, 1.464 was the actual answer given on their video. But we do have, you know, we got the answer 1.46 using numerical methods, you know, just guess and check in our calculator. Alright, so hell yeah. Alright, hell yeah. So what we have here is, now this is from black pen, red pen, you know what I mean? I don't mean to, you know what I mean, get a boost or anything, but it's just fascinating to take harder problems that people are doing on the internet. And what I like to do is this strategy. It's kind of the who cares, you know what I mean? It's like, let's not do it the way that they're going to do it with all the fancy steps that I'm never going to remember anyway. So anyway, so we're just going to try to figure out something about this. Now we got two different variables going on here, and we got integration. Now someone was saying, hey, can you make simple videos on integration? And this doesn't seem like a simple video, but I think it can be, because the heart of integration is to at least have an equation. Let's just say it's y is equal to x. That's probably the simplest one. And if you can think integration is just area under the curve, hell yeah, maybe it's that area. Maybe it's not that area, and it's the area between this and that. Maybe this is 5 and this is 4. So it's the and then you would say, hey, this is the integration between 4 to 5 of x dx. And the dx just means, sometimes that gets confusing. Like, what's dx? Well, it just means that you're multiplying two different things. If this is area under the curve, well, you're gonna have your equation right here, and then you have to multiply it by something else. So in general terms, you have your x and y coordinate system, and this is where this is important, because yeah, let's slow down and let's actually do an integration video just a little bit. I think integration, everyone knows it with velocity. If I say I'm going 60 miles per hour, technically that should be I already used the word technical, but that should be a technical term. It's like, hey, why do you know that so easily? Hey, I'm going 60 miles per hour. Even 60 miles per hour, it's two different things going on here. You have 60 miles, and then, you have 1 hour. You literally have two different numbers and two different units, but we still understand what's going on. So then when I ask the question, and this is fascinating, because if I ask the question, hey, if you go 60 miles, like, how far do you go? How long did it take you? I guess you'd have to ask that, how long did it take you? And you'd be like, well, it took me an hour. And then just looking at this is like, hey, this might be a harder one to integrate. But if I'm going 60 miles per hour for 1 hour, how far did I go? So let's do that. So we're going to have a scale here, that the y part and the x part, hey, the y part is going to be our velocity, and that's going to be in units of miles per hour. Okay, hell yeah. Now this are how far we went. Sorry. This is going to be in hours. Cool. And just to spell it out, if I have units of miles per hour, and then I have units of hour, what can I do to these two pair of units to get something useful? Well, we can multiply them, and then the hours cancel, and hell yeah, we get miles. So for here, it seems really useful to multiply these two things together. So that's basically what you do with integration. If this is my velocity, but you do it in kind of a unique way. So right here, I have units of miles per hour, and I have right here hours. Now if I was to multiply these two things together, that's technically what integration is. And we'll see it in a second. Now, we're just going to go for a constant velocity of 60 miles per hour. So I'm just going to say, hey, 60 is right here. Here's my velocity, miles per hour. You get it. And look at that. We go 60 miles per hour for, well, and then 1 hour is right there. Cool. And then who cares what happens after that hour? All right. So, so what we do is we find the area under this curve. You know what I mean? And when we do that, this, wait, let's see. Okay, so it's a square, you know what I mean? If this was a block of wood, let's just take this block of wood over here, you would measure this height, maybe 5 inches, and then you'd measure this height, maybe 6 inches. Cool, and you would find the area. Area is 30 inches squared, and you can do that. So with the y-x graph, you do the same thing, but this dimension right here, this side of this, imaginary wooden block is its dimensions are miles per hour, and you got a height of 60 of them. So cool. You not only have a number for this, it's 60, but then also it has units of miles per hour. Now this side, you know what I mean, is just 1 hour. And I think it'd be better if you actually came over here and did it, you know, to a side that's not close to the graphs. You're like, okay, so we have 60 miles per hour over here, and then we have 1 hour right here. So what is the area of this graph? The area is going to be, well, you just multiply either one of them together. So we'll just say 60 miles per hour, and then times 1 hour. Okay, hell yeah, and you get 60 miles. Cool. And this will really help you when, like, you're making mistakes, because you could do this. You could get this wrong and say, hey, I have a velocity of 60 miles per hour right here, but then I have a distance, so here's my xy, I have a distance of 60 miles. Now if I did this graph, this is going to be nonsensical, okay? Because, okay, I have, you know, and we'll just do it kind of fast. Hey, this is going to be 60 miles per hour times miles. Well, I guess we'll do it. We've got miles per hour times 60 miles. And look at this. We got 3,600 miles squared per hour. You know what I mean? So, I don't know. It really doesn't, yeah, so that's kind of a nonsensical thing. So it's always something to check. Now you could flip this number around. You could be like, okay, sweet, we have 60 miles. This is kind of fascinating. And you do this mentally all the time, but we're going to say, hey, I want to plot the inverse of velocity. So I'm going to say velocity to the negative 1. If you want to get technical, you could do 1 divided by velocity. Hell yeah. So we're going to have 1 divided by 60. Now, you know what I mean, obviously our scale on this thing, because that's way less than 1. So, I mean, if 1 was right here, 1 divided by 60 is right there. So, you know, even if 1 was right here, we'd have to divvy this up into 60 things, and that would be right there. So, let's just say this is 1/60th, and I think you get it. And we have hours per mile. So those switched. And yeah, sure, heck yeah, we can have distance down here, 60 miles. So now when we integrate this, we get 1/60th of an hour per mile. And then right here we get 60 miles. And so the area of this is 60 miles times 1/60th of an hour per mile. And then miles cancel, and hell yeah, we got 1 hour, you know what I mean? So kind of interesting, but I've had to use this, kind of this strategy for more technical problems, where you're just like, what is integration again? You know what I mean? And it's always the area under the curve. Everyone says that, but I'm doing one step better and saying, hey, we're multiplying these two things together. Okay, hell yeah. So that was a little, you know what I mean, that was a complete video. I'll do that one 1,000 times, because that was pretty good. It's always good just to know area under the curve is multiplying whatever the units are on the y and x axis. Okay, let's move on to this. Alright, booyah. So, yeah, we have a lot going on here, you know what I mean? Because you have two variables, and you're like, so, you know, what does this even mean? Well, you have two variables, but your primary variable is this. You know, if we have an equation that's y is equal to x, if we integrate it, we do integration of y is equal to x dx. You know what I mean? So it has to look like this. And so that's kind of what we have. We have, you know, so this x is just a number. You know what I mean? So I would like to do this like this. Anytime, you know, one of your variables is just kind of maybe a number, just make a little box. So we have box to the t, and this is our equation. So heck yeah, y is equal box to the t. That's kind of what my primary strategy is, like, before you dive into the technicalness of like what you can do to manipulate numbers. You know what I mean? Get a sense of what the graph actually is. You know what I mean? Because this is fascinating. And we're going to do a little 5-minute on this thing. Because just in general, we're going to compare these two things. We're going to say y is 2 to the x. So see how we threw in the number 2 here? And then we just changed the variable to sensical variables that we're all used to. You know what I mean? Anyway, and then check out this. So y is equal to x squared. Now, I'm going to pay you for 3 days. And at the end of each day, you get this many dollars. You know what I mean? You know, it's very part-time work. You know what I mean? You're just going to come in and just do hardly anything. But cool, I'm going to pay you. But I'm only going to, actually, you know what? I'm going to pay you for 4 days. You know what I mean? In 4 days, you know, you get to choose your salary. Do you want this one or that one? And check this out. I'm even going to, let's see. Yeah. Because, in 4 days, which salary would you choose? But, yeah, I'm going to even challenge myself. In 5 days, which salary would I choose? Well, if it was 5 days, I think I still would choose this one. So let's explore that. You know what I mean? Because after day 1, it looks like here you're getting 2 to the 1. Cool. Well, actually, I'm going to pay you on day 0. You're gonna have a starting day. So this is 2 to the 0, and hey, you actually make some money. Cool. So you actually get $1. Okay, 2 to the 0 is $1. Oh, so I might actually change. Yeah, this might be fascinating. This will be a good thought experiment. Okay, so now this one, 0. Hey, oh, you know what I mean? If you chose that out, you don't get no money. No money there. So yes, you're up $1 on this one. But then after the next day, we're going to have 2 to the 1. Cool, you make $2 here. But here you're only going to make 1 squared. Ah, damn it. You know what I mean? You're not making very much money over here. And let's do a running total. So right here you're up to $3. Over here you're just at $1. Okay, so maybe my thought experiment's not working out for me, but we'll see if it takes a turn. Okay, so now day 2. Okay, so with this we make $4 and we're up to 7. What happens on day 2 over here? 2 squared. We make hey, we at least made the same amount. So we're up to $5 over here and $7. Cool. All right, so now on day 3, so we have 2 to the 3. 2 to the 3, what the hell is that even? That's 2 times 2 times 2. That's 4 times 2. That's 8. Okay, sweet. And now we see a pattern. You know, 2, 4, 8. We can just kind of keep that pattern. And hey, we got $8, so now we're a total of 15. Day 3. Now over here... Alright, hell yeah. So over here we got 3 squared. Oh, check this out. We got $9. You know what I mean? Okay, hell yeah. Now we're doing things. And that means we're up to $14. Okay. And yeah, it's just fascinating because we wanted to know what the hell happened on day 4. So here we got 2 to the 4. That's just following our pattern. This is going to be 16. And so money-wise... and are we doing the right thing? Yep. Oh, yeah. So we get $1 there. Add 2 is 3. Add 4 is 7. Add 8 is 15. Add 16. We get $31. Sweet. But, okay, let's see what happens over here. This is 3. What am I doing? No, this is 4. This is day 4. So we got 4 squared. Oh, this is also 16. Okay, so we're still just a little bit behind on this one. Okay, so after 4 days, this one was the way to go. That's not what I was planning on. But anyway, I guess that's what happened, though. As long as you get paid on day 0, then, yeah, this one was always better. Interesting. Alright, hell yeah. So I totally forgot about this one. Yeah, we'll go a few more days, you know, see what happens. So in the 5th day, because this thing kind of goes back and forth a couple times. So 2 to the 5th, what's that? That's 32. And, oh, I got like ink all over. So anyway, so that's 32. So now we have 63. Cool, so we're up to $63 on day 5. Over here, we have 5 squared. And that's 25. Why isn't this representing? Oh, you know what? Oh, this is fascinating. I'm already doing the integral, and the integral is already already way. Yeah, the integral is always way better over here. Oh yeah, so I'm doing two different problems. So yeah, this will never catch up. And then over here we have 55. Okay, and then after this thing is just going to blow up. So we're going to go to our graph, and we're going to go, we're going to go 0 to, I don't know how far we should go, maybe 50. And then we're going to go 0 to at least 16, and then we'll go 0 to 5. Alright, so here is the 2 to the x graph, and then here, and we'll go to 20, I guess. So here's the 2 to the x, and then here is the x squared graph. Now, I guess this is fascinating. What I was doing was actually the integration. You know what I mean? We were figuring out how much we made that day, and then putting it into our bank account, finding out how much we made the next day, and then adding that to our bank account. And it's what we added to the bank account, which was that was the integration part. So that was fascinating, because it's with these equations, it's just interesting. Like this one blows the hell up. You know what I mean? If we have let's say you just have 10. 10 squared is 100, but 2 to the 10. You know what I mean? What do we know about 2 to the 10? Or this is a good one to know. 2 to the 10 is 1,000. It's so close to 1,000. Or no, damn it, is it 10,000? I always forget. You know what I mean? Yeah, I always forget what this is. I think it's just 1,000. Yeah, I think it's 1,000, but let's do it. So 2, so it goes 2 to the 1 is 2. So 2 to the 2 is 4. Then 6, 8, 30, 16, 32, 64. This is always a good one to do. It's hard to, once you double this, well, it's 128. You know, I think you could do that. Now here it's 125 squared. That's going to be 250 plus 6 extra, so it's 256. And then, you know, it's 250, not squared, but times 2. So 250 times 2 is 500, so we have 512. And then, hell yeah, 512 squared, not squared, but times 2 is 1,024. And then, so this is 2 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, shoot. 2 to the 1 is 2. 2 to the 2, 3, 4, 5, 6, 7, 8, 9, 10. Why am I messing this up? Holy Toledo. 2 to the 10 should be this one. Why am I saying it's... What error did I make? 2, 4, see, I did, yeah, see, there's my error. So there you go. 2, 4, 8, 16, 32, 64. So 2 to the 10 is this one. And it's super close to 1,000. So this is always one you should put in your pocketbook, that 2 to the 10 is basically 1,000. So that means 2 to the 20 is, unless, like, could you do this one? You know, because isn't 2 to the 10, isn't that just 2 to the 10 times 2 to the 10? You know what I mean? Can't we say this? Isn't that just 2 times 2 times 10? Or I guess you would, I think more easily you would say that's 2 to the 10 plus 10. Heck yeah, so that's 2 to the 20. So 2 to the 20 is a million. You know what I mean? 10 to the 6. Close enough, right? Is going to be 124 times, or I mean 1,024 times 1,024. You know what I mean? So it's 1.05 million, but you get it, right? All right, hell yeah. But this would have worked if we, hey, you're not getting any money on day one. You know what I mean? If you're not getting that dollar on day one, this becomes 2. So we have $2, $6 total, $14 total, $30 total, and $62 total. So if we compare these, shoot, are we still higher on this side? Yeah, but on day 4 we're at least even. Yeah, that's fascinating. But then the individual days. Alright, so no, this is good, you know what I mean? I'm totally messing this up, but that's why we do this. You know, we're looking at the graph, and yeah, this 2 to the x actually is higher because it starts at 1. And because it starts at 1, but it's kind of slow to, you know, to just blow up. And so, right here, at day 4, or at day 2, they're the same. So at day 2, these are both the same. And then this one, x squared, is higher. You know what I mean? So some math problems, they'll have, you know, comparing these, and you'll have this, you'll have where this graph is larger than this graph, even though that this, you know, 2 to the x is just stacked to where this blows up, you know, quite easily. And then we'll just do our window, and we're just going to go up to like 10,000, and we'll go over to 10 to the 6, and kind of, whoa, that was too much. And we'll, oh yeah, no, we just go in our x direction probably up to 50. All right, so we're gonna graph that. So this one blows up, and then the other one, this x squared, you know, it actually, you think x squared kind of blows up, but not compared to other things. 2 to the x for sure just goes straight towards infinity. This one kind of takes its time to get there. Alright, hell yeah, so we're back, and man, I apologize about that demonstration, but that was good because we learned about integration. If we're finding the area under the curve, the blue line is always, the area is always way bigger than the red line. Even though at any given day, between day 2, 3, 4, you know what I mean, hey, you're going to make less money if you chose... if you chose 2 to the x, you know, between those days. On day 3, you're only making 2 to the 3, you're making $8, where on this day, you're going to have 3 squared, heck yeah, you're making $9. So I guess that's the only thing I wanted to point out there. Alright, so let's continue on with this. We're going to try to solve this just using this idea of something to the x. Like this is our equation. Cool. So we're going to say y is, you know what I mean, some number to the x. Well, let's just choose a number. So a lot of the complex problems where, you know, I have this method where I either choose like 0, 1, or 2, you know, or the other direction, -1, -2, just to get an idea of what's happening with the problem. And so kind of we're going to do that same concept. We're just going to choose y is 2x. And see if that solves it. You know what I mean? So what this says is, and then for this problem, let's just graph that again. So when we have 0, x is 1. So we got the point right there. And then, so we'll just make a bunch of lines. Okay, sweet. And then, so then at x is equal to 1, we have 2 to the 1, that's 2. So right where we have 1, we're going to go up to 2, so sweet. And then we're going to do x is equal to 2, that's going to be 4. 1, 2, 3, 4. And this is all we're integrating from. You know what I mean? So here's the equation, right, of that line. And we're integrating from 0 to 2. It just says find the area underneath this. And so what I'm going to do is just make boxes and see if we get close, because there's a box. There's a box, and that's actually a complete box. So there we have 3 boxes. So we know that the integration from 0 to 2 of y, which is the integration of 0 to 2 of 2x dx, or y dx, you know what I mean? The integrations of these is just the area under the curve between 0 and 2. And so we have more than 3. So this is going to be bigger than 3. So our answer is wrong. Okay, so now what I do, you know what I mean, it's kind of like the mountain climber approach. Hey, let's just throw in y is equal to 1 to the x. Okay, this should be easy because we have 1 to the 0. That's going to be 1. So at 0, we're up to 1. And then when we throw in 1 to the 1, that's going to be 1. And then at 2, we're going to do 1 to the 2. Well, 1 to any number is just 1. Okay, sweet. All right, so now the area under this curve of this line, so this is y is equal 1 to the x, and then we're going to integrate it. So we're going to basically say integration of 0 to 2 y of dx. That's going to be the integration 0 to 2 of 1 to the x dx. And even if you don't even know why you even do like the dx part or what the hell's going on, just know it's just like, well, I guess you're just multiplying, you know, two things. We have this this x component that you're multiplying, so we're going to multiply this side and by that height. And the height is basically the equation in itself, you know what I mean? And how that works out is like, well, over here, you know what I mean, hey, this is the height of the equation, and this is also the height of the equation. So this is where, you know, if this was a linear line, you could just kind of take the average and call that the height. You know, so that happens quite a bit. But because this is a curved line, you can't do that. But we did it pretty visual. So all right, so we get an area of 2. So this is equal to 2. This is greater than 3. And so now what we do know is that the answer, you know, almost 100%. So even if it's a hella complex problem and you're not knowing what the answer is going to be, it's just like booyah. We know that this box, you know what I mean, is going to be in between 1 to 2. It's going to be somewhere in between that. And I don't know, you know what I mean? Should we do at least one more and just use our calculator and say we're going to go box to the, we're going to say y is 1.5 to the x. And so let's do this. So we're going to 1.5 to the 0. Anything to the 0 is always 1. So we're going to go 1 there. And then we got 1.5 to the 1. That's just going to be 1.5. All right, heck yeah. So we're going to go 1 to 1.5 right there. And then at 2, we're going to have 1.5 squared. That's going to be 2.25. So kind of right there. And let's see what we got. So we have a couple boxes. And then what do you think? You know what I mean? Hey, this looks like almost like 2 this way, 1 this way, and it's a triangle. It's a triangle with a base of 2, height of 1, well, what's the area of a triangle? Base times height 1/2, so it's 2. 1/2 of 2 is 1. You know, so hey, this is pretty darn close to 3. So just right there, we did 3 approximations, and we know more about this than most people. You know what I mean? Because I guess this is probably a hard one, you know, to do. And then what do we know about this though? What would this point be if we were if we hit this at the halfway? This would be 1.5, which it is. So that's 1.5. Yeah, this is fascinating. But it's increasing. So we do know that this thing is increasing this way. So that means that this thing is bubbled. So let's just do a bigger view. It means that if we're at 1.5 there, and then up, well, and this isn't even, oh, bummer, you know, my bad. This isn't up 1. This is up 1.25. So we actually might be a little bit bigger than 3. So yeah, so right now I don't know definitively, but also this thing kind of curves this way. But I don't know definitively if the answer is less than 1.5 or greater. I'm just going to go out on a limb, and because this goes up to 1.25, I'm going to say that the answer is greater than 1.5. You know what I mean? So I'm going to say whatever this answer is going to be greater than 1.5. Alright, hell yeah. And so that approach was just with a couple simple drawings. We didn't even really use our calculator except to figure out what 1.5 squared was, which you could have just done 1.5 times 1.5. That's 15 times 15. You know what I mean? What the hell is 15? See, sometimes 15 times 15 is hard. Isn't that just 10 times 15? And then 5 times 15? So this, like 15 times 15 should be pretty easy. You should just think 150. And then just think, well, another 150, but half that. So that's going to be 75. You know what I mean? So, but sometimes it's hard to do that in your head. It's just like, what is that? That's a 5, that's a 12, that's 225. Okay, so it's 2.25. Yeah, I got to get better on my, like, that type of math skills, that's for sure. Okay, so what we're going to do in our calculator, we're going to do 1.5 to the x, and then we're just going to actually do a window of 0 to 2. Well, I guess we'll go 0 to 3, and then we're going to go 0 to 3 in the y direction. Always good to figure out like where your graphs are. And so what we're going to do, oh, and I guess we're going to go -1. So yeah, let's graph this. And what we're going to do is we're going to integrate between 0 to 2. We have a function on our calculator that says integrate. So we have integrate, and then and then sometimes you can do this. You can go value 2. No, I'm sorry, value 0, and then we can do integrate, and then this is our lower limit, upper limit. We just throw in the number, so that's our upper limit, 0 and 2, and we get 3.08. So yeah, I was right that it was bigger. So now we're just gonna, we're gonna do 1.4. We're gonna graph that. We're just gonna do this. Like, a lot of people do not do this method because I don't know. It's like it doesn't get taught. It seems maybe like cheating or something. So we're going to do 0 to 2, and we're just going to see, and so that's obviously lower, you know what I mean, obviously. So how about just 1.49, and so we're going to graph that, and hopefully we're pretty darn close. Okay, so, and it's just good to get fast skills with your calculator. Alright, so now we really need to come down. So 1.47, going to graph that. Hopefully we're right in here now. Whoa. Alright, so just a little bit more. 1.45. Alright, let's see if that did it. Okay, heck yeah. So yeah, 1.45 worked. We'll go up to 1.46, and then probably just call it. You know what I mean? We'll graph it, and then it's going to be in between 1.45 to 1.46, hopefully. Whoop. Alright, no, it's higher than 1.46. And, so sweet. Yeah, I'm going to say, hey, that's pretty darn close. So it's just a little bit higher than 1.46, and booyah. So we kind of have an answer for this problem, you know what I mean? And I don't know, you know what I mean? I'm satisfied. We learned something about this equation, and at the end of the day, that's going to be kind of the most satisfying, is to be like, well, what complex math, equation are people actually working with? And I swear, most people won't actually look at the graph and analyze it to be like, oh yeah, no duh, that's kind of what's going on with that graph. Just because they're in the realm of, just kind of analyzing what you can, like methodologically like do with the numbers, and outside of that, so this is kind of like numerical methods. It's numerical analysis. And your calculator does this all the time. You set up programs where you're just kind of like guessing, either using an approximation, type of tool, or just literally, going back and forth guessing and trying to hone in on answers. So heck yeah. So I think I'm done with this. There's no way I'm probably solving this thing anyway. So booyah, we did it. Alright, thanks for joining me, and guess what? That's a video.